Alright, ladies and gentlemen, I think it's about time that we started another project here. Now, I know what you're probably thinking. Isn't the computer tutorial series computer technically a project? I wouldn't consider it a project. I would consider it more like a side project. So, the things that I'm doing here for fun, not for educational purposes, I would consider these projects. So, that said, yeah, I think it's time to start a new one here. And originally I was going to try and do the whole combination of Minecraft computers and x86 architecture, blah blah blah. That kind of became the computer tutorial computer thing. So what instead I'm going to be doing is bringing to life a challenge that was issued to me during the vlog stage of the Deep Thought project. And that is a challenge issued to me by Enderscythe. So hopefully I'm pronouncing that correctly. I think I am. He actually challenged me to build a computer to interpret a language that he wrote, which I thought was really interesting. Like, most challenges I receive are usually like, build it with size constraints, or build it with X amount of instructions, or build it with, build it diagonally, It's kind of, they're okay, but they're not, like, really cool challenges. This one I thought was awesome. Like, he wrote an entire language called Stackish, and I'll get to what that is in a sec, and he challenged me to build an interpreter computer for his language, which I thought was going to be interesting, because whenever I build a computer, I'm always building the language and the computer side by side, so they both kind of complement each other, which means I can utilize different parts of my computer and the language more effectively. I can optimize each bit in accordance to each other. But this time I'm building a computer to match the language, which means I don't have that flexibility. So it is a pretty interesting challenge. Yeah, but the language he asked me to make an interpreter for, Stackish, as the name would suggest, it is a language that revolves around the stack. Now, I know there's probably not a whole lot of you that'll understand what the stack is. So if you don't know what that is, you're probably going to get lost. But hopefully by the end of this, you'll have a vague understanding of what the stack is. Right. So his language basically just revolves around the stack, and that's it. Like, there's no data accessing. There's no complex instructions, there's no branching, there is branching, but there's no calls and returns, there's no interrupts. So it's a really interesting language, and it did catch my attention. That's kind of why I wanted to build a interpreter for it. Right, but his language consists of 28 commands, and they primarily revolve around pushing things onto the stack, or popping things from the stack, or unpopping them. That's an interesting one. But I decided to modify his commands just a hair. Hopefully he'll allow this, and he won't get super pissed, because if he doesn't allow it, I'm going to have to redesign this whole thing. But basically what I did was I kind of trimmed the fat from his language, because there are a few commands that were kind of redundant. Like, the first 10 commands are 0 through 9, and those basically push the number 0 through 9 onto the stack. And it doesn't like push 0 through 9 onto the stack. What it does is, if you put the number 3, it'll push the number 3 onto the stack. And then there's the next command, which are double quotations, and what those will do is they'll push everything between the quotes. That's my phone. They'll push everything between the quotes onto the stack. And so I figured that was kind of redundant, so what I decided to do is I decided to combine those 11 commands into one. And so what it is you can push immediate values onto the stack with the first half of the opcode representing that instruction, and then the next half actually representing how many characters you're pushing. So we can push up to 16 characters, of course, because there are 4 bits, 16 combinations, but that means that instead of pushing one character at a time, you can actually push up to 16 at a time. So that's just a way of leanifying those commands. And then there are other commands that I looked at and said, do we really need like 3 different versions of the out command? Because there was out as sorry about that. Just people giving me a call about stuff that's breaking because other people don't know how to take care of things. Yeah. So anyway, as I was saying, there are some commands I was looking at that I didn't think we really needed like 3 different versions of. Like the out command, there were 3 different versions. There was like out ASCII, out normal or out numbers, and then out string. I was looking at that, and I'm not really going to be working with ASCII, and I'm not going to bother just outing one character at a time. So I figured I just make out string and leave it at that, you know. But ultimately, what that all boils down to is I basically just modified the instructions just a little bit to kind of optimize the hardware. Because if I had gone with the language itself, you know, going command for command verbatim, the hardware would be a lot more complex. And so I'm just trying to make things as simple as possible here. Yeah, but then on the subject of the hardware, these commands really, they don't do much, you know, because they revolve around the stack and not much around the registers. There really isn't too terribly much need for those. So I basically have 2 temp registers, temp A and temp B, although the majority of the time you're using temp A. So temp B is only there for times when we need 2 operations to work on, like an operate, you know. So I should also mention that these registers are pretty much invisible to the programmer. Like normally in computers, you can have a command that says move to A or move to B. There's nothing like that. So these registers are only accessible by the microcodes. They are invisible to the programmer. So we got the 2 temp registers, we've got the program counter, as it says on the tin, and then we've got the stack pointers. Note I said stack pointers, plural. That's because there's actually 2 stacks with this computer system, which I thought was super cool. Also a pain in the ass to build, but still cool nonetheless. So there's the main stack pointer, and so that's going to dictate the position in the main stack, which is where data and addresses will be stored. And then there's the popped stack pointer. Now, I mentioned earlier that there's an unpop command. Basically, the rule of this computer is anything that gets popped from the main stack must be pushed to the popped stack. I know that's super confusing, but basically anything that comes out of there must go into here. And so what that allows for is when you perform the unpop command, it will take the top of the popped stack, pop it off, and then push it back into the main stack. So you can essentially undo a pop. It sounds useless, but if you read some of his examples in where that's needed, you can quickly see the use for such a command and such a feature. The only downside to this is, had I just had the main stack pointer and performed all my operations from that, I could have easily gotten a lot of these instructions down to maybe 3 clock cycles. But unfortunately, because I have to take the extra time to push the popped data to the popped stack, my longest instruction is like 5 clock cycles, which is still pretty good, but it's longer than I would have liked. But it's a trade-off, I guess. And then you might also notice that these pointer registers, they're missing some pistons here, and that's because each pointer register actually has a fixed page vector. So what that means is, even though this is an 8-bit computer, each register can't actually reach the full range of its address space. So the program counter can't actually count from 0 to 255. It can actually only count from, I don't remember what this is. This is 64, so it can only count from 64 to like 127. So it only has a 64 address range, and it's located like 3/4 of the way through memory. Likewise with the popped stack, that's kind of located more towards the beginning, and then the main stack pointer, that's located right at the beginning, but again, these 2 bits are kind of set to 0, so it can only access 0 through 63. So there's a reason for why I did that, just to make things easier, because ultimately we don't want the program counter to be able to access anything in the stack. We don't want the stack to be able to access anything in the program. So I did it that way so that that's just not a possibility. And it also saves on instructions at the beginning of the program because you don't have to initialize the registers. And then as far as operations are concerned, I actually like this because most of my computers have at least 8 functions. Some of the more advanced ones will have 16. This one has 3. So technically 3. So it has 3 commands that uses the ALU here, and they are add, subtract, and compare. Well, here's the thing. Compare is really just a subtract, so there's only 2 commands that this ALU needs to do is add and subtract. So it's literally just an adder. So there's not much there, which I guess is good because that means there's not a whole lot of control lines. Like, this is the only control line for the ALU. But other than that, you know, it's not much to say about that, I guess, you know. But there are actually 2 adders. So there's the processing adder, which will take the data found in the A and B register and add them together. And then there's the address adder, which will take the value from either the program counter, the main stack pointer, or the popped stack pointer, and either add 1 or subtract 1 and feed it back into that register. And it will then either take the pre or post operated address and stick it on this bus, and this bus will determine what part of memory we are accessing. And then that's pretty much it for the operational side of the hardware. I mean, there's some small things, like there's a random number generator, there's an address mux over there, but they're small details. They're really not that important. And then you might also be wondering why I move the... Well, actually, you know what, I'm going to go over that. So, one thing I usually do when it comes to these buses is I'll have the in bus down below, I'll have the out bus up above, and then I'll have the address bus in the middle, and then I'll just send it out in a direction, and then I'll connect RAM off to the side. The problem with that is those 90s are really difficult to do. So I figured what I'd do instead is I'd actually just get a 90 out of the way right off the bat. So the address comes out, it 90s off, and it goes off to the side. And then the RAM is actually going to be connected directly to these buses. So that will reduce the distance that the RAM data has to travel to get from RAM to the CPU. And then I already put the address off to the side, so that can hook up directly to the decoder, which will, you know, hook up to the RAM, which will select addresses for me, and then I can read from and to accordingly. Yeah. But then, of course, because RAM is just kind of butt up right up against the CPU, there's no room for I/O, which is why I actually decided to put another expansion bus on the other side of the CPU. So I/O will be connected to here. Now at this point, this particular CPU doesn't require an address for the I/O, so that's why the address bus isn't coming over here. But in future, that's probably something I'll need, so I'll need to try and figure out how to get the address bus over there without cutting through all of this, because that's going to be a pain if I have to do that. But I think doing it like this in future will probably be more beneficial because it means fewer 90s in the data buses, which means data can travel to and from the CPU a lot faster. And then on the subject of speed optimization, I kind of want to go over this. Now that we're done with the operational side, we can look at the control side. So you might recognize this as a more traditional Minecraft program ROM. Now, I said a while ago that I wanted to try and combine x86 and Minecraft computers because Minecraft computers, or traditional Minecraft computers, are actually a lot faster than mine, but my computer designs are a lot more powerful because they're x86 derived. So what I initially tried to do was I tried to jam-pack a Minecraft computer with x86 features and just leave the ROM as it is. And I'm going to be honest with you, I don't like this. I really don't. So what I ended up doing was I went the other way. Instead of jam-packing the computer with x86 functions, I just modified the control to match a traditional ROM. And I'm liking how that turned out. I actually did that with SkittleBits Mark II, or SkittleBits Revision 2, with its state machine-based control logic, and I'm going to be doing it with this as well. And the reason why is this is actually probably the cleanest way of programming your wires, your control lines. But I hate programming these things. I really do, because if you program a computer like this, you only have to remember 8 bits, and they're usually encoded. So sometimes you only need to remember 2 bits, and then the next 6 bits determine variables. Versus this, this is just a small computer, but this has like some 20 lines, and you have to sit here and go, okay, in this instruction, I want to read the PC, and I want to read A, and I want to subtract, and that's going to go out, so I want to read I/O or write I/O or whatever, and you have to go through and you have to set each bit, and that's just a pain. So I don't mind doing it once, but if I want to reprogram this computer to do something else, I don't want to have to go through and replace all the torches. That's just a pain in the ass. So I'm doing it this way because it's cleaner, but the way I'm going about this is going to be much different because this is more like a set and forget system. So what I've got is 24 lines, and they're all pre-programmed, but these are not a program per se. What these are micro instructions. So each one of these lines represents a move of some kind in the computer. And the reason why I did this is basically what I did, and I'll have an image popped up of the spreadsheet, is I basically just wrote down all of the instructions that this computer will perform, and then I broke them into their individual steps. Like, for example, if I'm going to be, let's pick one. If I'm going to be sending data out, right, I need to be able to, I can't just say send data out, because it doesn't quite work that way. It takes multiple steps, because I am popping stuff from the stack, and then I'm pushing it out onto the popped stack because it's been popped, and then I'm sending it out. So I have to pop the value, which means I need to decrement the stack pointer. I need to move it to one of the temporary registers. Then I need to push it onto the popped stack, so I need to increment that stack pointer, move that temporary value into memory, and then I can move it out into the I/O bus. So obviously that's 3 move operations that occur, which means that's 3 micro instructions that need to happen. So in this ROM, I guess, are all of the micro instructions that this computer is going to use. And they're not in any particular order. Basically, one line represents one kind of move operation that this computer can do. And none of them are the same. So even though there are some micro instructions that are used across multiple instructions and used multiple times, like, for example, let's see if I can find it. Just give me a second. Where is it? I'll find it. Yeah, whatever, I don't know if I can find it. It's like this. So it says stack pointer minus minus move over to B, but it's actually A. That one's used like 8 times across the entire instruction set. So rather than having 8 instances of something like that, oh, there it is. Yeah, so rather than having 8 instances of something like this, I actually just add it once, and then any time an instruction needs this particular microcode, it can just activate the line for a clock cycle. When it's done, it turns it off and moves on to the next one. Yeah, so basically when an instruction is executed, and I'm going to do my damnedest here to try and explain this coherently, but when an instruction is executed, it's basically going to pick out a certain number of micro instructions that it will execute, and it will execute them in a certain order. So basically, like if I were to do like an add, it's going to look at it and go, okay, well, I'm going to need 5 microcodes. I'm going to need this one, this one, this one, this one, and this one, and they're going to be activated in this order and in this timing, and as a result, the appropriate microcodes will be executed, and the appropriate lines will turn on at the appropriate time, and the operation will be executed. So yeah, and like I said, this is basically like ROM in a traditional Minecraft computer, except we're not moving in order. So we're not starting there and going like this. It's kind of going to go all over the place. Yeah. So rather than hooking it up to a program counter and hooking that up to a decoder, instead what we're going to be doing, what will dictate what lines get turned on when, that will be dictated by the state machine. Oh boy. Yeah, so similar to what I did over there in Skittlebits Rev 2 is a state machine is going to be controlling everything for me. It's just this time around I'm doing some optimization work to try and reduce the size of both the state machine and the control ROM. So in the last version I didn't compress the control ROM, so if there were multiple instances of the same microcode, there were multiple lines that had the same microcode on them. So I've rectified this by condensing all duplicate microcodes into one line. And then the finite state machine, I actually haven't designed that yet, so I don't know what it's going to look like, but I can at least tell you that when I designed it, I'm going to try and consolidate as many strings of microcodes as possible. So instead of having one branch for every instruction, which wouldn't be too hard because there's only 17 instructions, but instead of having one branch for every instruction, there will be one branch for every instruction that has the same start. So, for example, pop, out, add, subtract, compare, jump, and jump if stack pointer is empty. Those all have the same first two microcodes. So those will all share the same branch up until the third microcode, at which point there will be sub-branches. So that will hopefully reduce the size of the finite state machine and make it a little bit easier to squeeze in here. But like I said, I haven't designed it yet, so I don't know if that's going to be practical. But what I figured what I'd do is I'd show you the ROM without the state machine, because I had actually gotten a few questions about the state machine. Not a whole lot of people understood it, and so I figured what I'd try and do is I'd break it down a little bit. So what we've got, like I said, just to reiterate it one more time, we've got a ROM that sends control signals into the computer like a program ROM in a traditional Minecraft computer, but instead of going in order, it goes out of order, and that is dictated by the state machine. And the state machine I have yet to build, so I'll have to build that, and we'll have to discuss it in the next video. Yeah. So that's basically what I've got so far, is basically just the ROM with all its microcodes and the hardware. Yeah, so I figured I don't have all of these tested. I'm still doing some extensive testing and such, but what I can do is at least show you its ability to push a random number onto the stack. So I've got one microcode that's specifically designed to do that. Random number pushed onto stack with the stack pointer incremented. So it's a push. Anytime it's incremented, it's a push. If it's decremented, it's a pop. Not traditional, I'll tell you that right now. In Intel microarchitecture, a push is actually decrementing the stack pointer, but I did it this way for simplicity's sake. But if I actually go ahead and demonstrate a clock cycle, so that turns off, indicating that the clock is now active, what will happen... this happened again last time, and I'm not sure what's causing it, but just give me a sec, I need to reset this. Okay, it's been reset. I don't know what's causing that. I think there's some sort of conflicting command blocks somewhere that's causing it to teleport down when it really shouldn't. Or maybe it might just be the address. I don't know. I'm still trying to figure all that out. But point is, when the lever's flicked down, representing the upcycle in a clock, the address is pushed out. This is indicated by the armor stand moving out to its appropriate position. So right now the stack pointer is pointing right here, which is where the armor stand has moved. And then the data that is being moved into the memory, which in this case is a random number, is being generated by the random number generator, pushed onto the bus, and sent out into this command block contraption, which will actually convert it into glass and stone. So then on the falling edge of the clock, this line will be deactivated, and what will happen is the data will be copied from there to memory, and the address will be reset, so we can actually watch that happen right there. And I don't know why it stopped there. Something's seriously buggy with this. I'm going to have to figure all this out, but that's something for later, I guess. Yeah, so I don't know, maybe we could try it again, see if it works. Yeah, I suppose it's moving. Yeah, so if I do it again, I can push another random number, and it goes back to there. I don't know why it's going back there. Oh. Yeah, so that's basically it. So one thing I do want to point out, and this is something I'm actually really, really proud of, is the last time I did something like this, well, the only other time was with the SkittleBits Rev 2, and I explained this in the experimenting with control logic video, link to that, I guess, somewhere. But in that computer, well, I suppose I should probably explain this real quick. So, real quick terminology lesson. Clock cycle, that's one cycle of the clock turning on and then turning off. Bus cycle, that's the cycle of sending an address out and then transferring data on the data bus. And then an instruction cycle is just an instruction cycle. Yeah. So, basically, with the SkittleBits computer, one bus cycle equated to 2 clock cycles. And the reason why was because I needed to take one clock cycle to actually send the address out, and then another clock cycle to actually transfer the data. As a result, if an instruction required 3 bus cycles, it required 6 clock cycles, which kind of slowed it down a bit. But here, what I've got now is I've got this computer set up so that a bus cycle equates to 1 clock cycle, which theoretically means that I can double the speed. So this thing should work twice as fast as the SkittleBits Rev 2 version. So what you saw when I flicked this lever, normally that would have taken 2 lever flicks. So I would have had, if I wanted to push a random number onto the stack with the last model, I would have had to push 1 lever, which would have pushed the stack pointer address out onto the address bus. And then once that was done, I could turn that off and then generate the random number, push that onto the bus, and then write it to memory. But with this, you'll notice I can actually do it with just 1. So in 1 foul swoop, we generate the address, and on the falling edge, it is written. Yeah. And that's actually exactly how I was able to do that. It was a bit of a trick, but what I had to do was I had to separate the pointers from the general registers in terms of their bus. So these are technically totally separate registers. So the pointers get their own independent bus, which they can then use to calculate addresses, or calculate update addresses, I guess, and then send the address out. And what this means is when I flick the lever, and I'll do it again, what's going on is, first, I don't know how to explain this. The pointers are doing their thing on the address bus, and the registers are doing their thing on the data bus. So this is all happening kind of in parallel. So yeah, I really don't know how to explain this. Like, it makes sense in my head, but the words, they know do good come out of mouth, if that makes sense. It really shouldn't. Yeah, so when you flick the lever, what happens is the registers are being read from, the pointers and whatever registers are holding the data, and those pieces of information are sent down 2 different buses. So the first bus is the address bus, and the address gets sent down the address bus, and that passes through the adder and then gets sent back so that the register can be updated with the next address. And then, of course, the address is then sent out into the address bus itself. And then at the same time, the registers are being read from, and its content is spewing out into the data bus and being sent onto the data out bus over here. And then, similar to the computer tutorial series where writing happens on the falling edge, at this point, because we have this signal over here for memory write that's inverted, it is now primed to write, but it hasn't written yet. Only when the signal turns off will the data from the data bus actually be copied into memory. And then you might be thinking, well, won't the address suddenly change when that happens? I'm hoping that the delay with the address bus will rectify that issue, but you never know. So, like I said, if I go ahead and just turn that off, the data is pushed, and the address is updated. But yeah, like I said, this basically means that in bus cycles, they only take 1 clock cycle, which means they only take 1 state, which means that my finite state machine can be smaller. My lookup table for control lines, it can be smaller, and because I'm using half as many clock cycles, this should theoretically be faster. hopefully. Yeah, so hopefully that wasn't too much for you guys to take in. I know that was kind of a lot of advanced stuff thrown at you very, very quickly, but hopefully it made some sense. And so I guess, yeah, this is pretty much the progress of the Stackish interpreter thus far. And then up until now, I've always had like a fun, funky name for these computers that I would label, So my last computer, Deep Thought, I had, already named by episode 1 of the vlogs. So I would say, the Deep Thought vlog. I don't have a name for this. It's kind of difficult to come up with one, so I'm gonna have to come up with one later, and then just change the titles on these videos accordingly. So for now, I'm just gonna call it the Stackish interpreter vlog, episode 1 or part 1 or whatever. But yeah, that'll have to change in the future. And then as far as the language is concerned, like I said, this is kind of Endersight's challenge. So he kind of dictates the rules. So hopefully he's okay with me changing the language a little bit. Yeah. If he's not, like I said, this is all for naught, and it's back to the drawing board, and I have to make the computer actually run the language, which will be super fun. Not. Yeah, but I guess the next step, assuming all goes according to plan, is I need to design the finite state machine. And that'll be interesting. We'll see how that goes. I'm hoping that it goes well. And once I get it designed, I actually want to try my best to explain how that works to you guys, because I think this system of control lookup tables and finite state machines is actually a far better system for controlling your computer than just a standard program ROM. So, it may not be as fast. It takes time to fetch the instructions, but it's a hell of a lot easier to program than this crap, I'll tell you that much. So yeah, hopefully you enjoyed, and I will see you guys in the next video. Bye.